Welcome to our video on the derivation of equations of motion. These three fundamental equations allow us to describe the motion of objects with constant acceleration, which is essential in physics and engineering. Before we dive into the derivations, let's define our variables. U is the initial velocity, v is the final velocity, I is the constant acceleration, t is the time elapsed, and s is the displacement. Let's begin with the first equation of motion. By definition, acceleration is the rate of change of velocity with respect to time. Mathematically, we can write this as A equals change in velocity divided by change in time. Rearranging, we get A times t equals v minus u, which gives us our first equation of motion, v equals u plus at. Now, let's derive the same equation graphically. Consider a velocity-time graph for an object moving with constant acceleration. At the starting point, time is 0 and velocity is u. At the end point, time is t and velocity is v. Since acceleration is constant, the graph is a straight line, and the slope of this line equals the acceleration, a. Using the slope formula, rise over run, we get A equals v minus u divided by t. Rearranging gives us v equals u plus at, confirming our first equation. Now, let's move on to the second equation of motion. For constant acceleration, the average velocity is equal to the arithmetic mean of initial and final velocities. This can be written as v average equals u plus v divided by 2. We also know that average velocity equals displacement divided by time, so v average equals s divided by t. Equating these two expressions, we get s divided by t equals u plus v divided by 2. Multiplying both sides by t, we get s equals u plus v divided by 2 times t. Now, we can substitute our first equation, v equals u plus at, to get s equals u plus at divided by 2 times t. Simplifying, we get s equals u plus u times t plus at times t divided by 2, which gives us our second equation of motion, s equals ut plus 1/2 at squared. Let's derive the second equation graphically as well. From our velocity-time graph, we know that displacement is equal to the area under the velocity-time curve. This area is made up of a rectangle with height u and width t, giving an area of u times t, plus a triangle with base t and height v minus u, giving an area of 1/2 times t times v minus u. So the total area, which represents displacement s, equals u times t plus 1/2 times t times v minus u. But we know that v minus u equals at from our first equation. Substituting, we get s equals ut plus 1/2 at squared, confirming our second equation. Finally, let's derive the third equation of motion. We want to establish a relationship between initial velocity, final velocity, acceleration, and displacement without explicitly involving time. Starting with our first equation, v equals u plus at, let's square both sides. This gives us v squared equals u squared plus 2 times u times at plus a squared times t squared. From our first equation, we can express t as v minus u divided by a. But we don't want to substitute just yet. Instead, we'll rearrange our second equation, s equals ut plus 1/2 at squared, to solve for at squared. This gives us at squared equals 2 times s minus 2 times ut. Now, substituting this into our squared velocity equation, we get v squared equals u squared plus 2 times u times at plus a times 2 times s minus 2 times ut. Simplifying, we get v squared equals u squared plus 2 times a times s. And this is our third equation of motion, v squared equals u squared plus 2as. Let's tackle the third equation graphically as well. While this equation is more complex to derive purely graphically, we can use our previous graphical interpretations to help us. We know from our first equation that at equals v minus u, and from our second equation's graphical derivation, displacement s equals ut plus 1/2 at squared. Now let's rewrite at in terms of v and u. At equals v minus u, so at squared equals v minus u squared. Substituting this into our displacement equation, we get s equals ut plus 1/2 times v minus u squared divided by a. Solving for 2as, we get 2as equals 2 aut plus v minus u squared. With some algebraic manipulation, this gives us v squared equals u squared plus 2as, our third equation of motion. Let's summarize what we've learned. We've derived the three equations of motion both algebraically and graphically. First equation, v equals u plus at. Second equation, s equals ut plus 1/2 at squared. Third equation, v squared equals u squared plus 2as. These equations are incredibly useful in physics for solving problems involving objects moving with constant acceleration, such as falling objects, projectile motion, and much more. Thank you for watching, and I hope this derivation helps you understand the equations of motion better.